Hello everyone. I'm going to this evening study Rust. I tried to study it multiple times, but every time that I was studying it, I was getting angry on it and stopping to do it. So this time I'm going to overcome my rage. My rage quitting desires and try to go through it. So I asked AI what would be the best way for me to learn it, and AI suggested me Tour of Rust. So let's go through it.
Welcome to the Tour of Rust. This is meant to be a step-by-step guide through the features of the Rust programming language. Rust is often considered a language with a steep learning curve, but I hope I can convince you there's a lot to explore before we even get to complex parts. You can also find this guide in these languages.
Okay, I'm already lost what to do. There is a next button. Okay.
In this first chapter, we're going to be exploring the very basics with functions, variables, and the most primitive types. Glad to have you on board. Also, in case you are wondering who this adorable crab who is speaking to you is, I'm Ferris, the unofficial mascot for Rust programming language. Nice to meet you. Once you get familiar with Rust, you can call yourself a Rustation. That's how people who use, contribute, or are interested in Rust call themselves.
No, I don't want to become a Rustian.
This tour uses an interactive coding tool from Rust Playground. It's a great way to play around with Rust and show others your creativity and challenges.
I wish something like this would be made for C++. Compiling, finishing div, welcome to playground. Okay, so what is it? A fan main println. Why there is a exclamation mark here? Fn, got it.
Variables are declared using the let keyword.
Let. Okay.
When assigning a value, Rust will be able to infer the type of your variable 99% of the time. If it cannot, you may add the type to your variable declaration.
Okay.
Notice how we can assign to the same variable name multiple times. This is called variable shadowing, and the type can be changed for subsequent references to that name.
Variable shadowing. So you can do variable shadowing. And the compiler would not complain. And compiler did not complain. I don't think variable shadowing is a good idea.
Notice how we can assign to the same variable name multiple times. This is called variable shadowing, and the type can be changed for subsequent references to that name. Variable names are always in snake case.
This was making me rage quit. Always in snake case. It's like it's so opinionated. Like there is no other way. Always snake case. Rust can also declare the and initialize later, but this is rarely done. What if I comment this thing out? Let's program type annotation needed. Consider giving X the explicit type. Okay, let's see. Oh my god, it's a tabs. Okay, whatever. Let's see. Let hello world equals 10. What is it? If this is an intentional prefix, it with underscore hello world warn of by default warn variable should have a snake case name. Should have snake case name. Oh my god. Playground brain playground warning run cargo fix pin players applied one suggestion. How about hello world. Nope, doesn't like it. What if I want to have a constant? Anyways, so compiler does not allow you. Oh, so one warning. What is warning? Unused. Okay, so let's do print hello world. Still not happy. Oh, semicolon is missing. Okay. 42. And let's do hello world like this. Yeah. With similar name exists. Oh. Okay, so would it work? Converted into snake case. Yeah, so it's a strictly snake case. Like a variable is snake case, nothing else. Yeah, I'm not going to rage quit. But it's like, okay, snake case, whatever.
Rust cares a great deal about what variables are modifiable. Values fall into two types. Mutable, the compiler will allow the variable to written to and read from. Immutable, the compiler will only allow the variable to be read from. Mutable values are denoted with a mut keyword. We will have more to say on this concept later, but for now, just keep an eye out for this keyword.
Look, why it's a let mut? Why it's not just a mut? It's like, why we need to put two keywords here? It's like, what the garbage is this? Why is a let mut? Just make it mut. I don't know. I don't know. Maybe it's, yeah. Anyways, maybe it's fine. Maybe it's fine. And the funny thing, they allow to do shadowing, right? Let mut x equals 0.1, 1.1. Oh, mut. Does it have a shortcut key? Okay, so now it's remove this mut part by default. Why it's not happy now? Compiler playing around, not this part. By default warning value assigned to x is never read. So it's a warning. So let's do it like this again. Still, variable does not need to be mutable. X times equal to strong typing. I guess it's good. I'm not mad at this part, but I'm mad at this part. Shadowing, variable shadowing. It's not good. This is not good. Anyways, let's go.
Rust has a variety of familiar types. Boolean bool for representing true/false. Unsigned integers U8, U16, U32, U64, U128 for representing non-negative whole numbers. Signed integers I8, I16, I32, I64, I128 for representing whole numbers. Pointer-sized integers usize, isize for representing indexes and sizes of things in memory. Floating point F, 32, F64. Characters char for representing a single Unicode character. Tuple value for passing fixed sequences of values on the stack. Arrays value, a collection of similar elements with fixed length known at compile time. Slice is a collection of similar elements with length known at runtime. STR string slice text with a length known at runtime. text might be more complex than you are used to in other languages. Since Rust is a system programming language, it cares about memory issues you might not be used to. We will be going into this in detail later. Numeric types can be explicitly specified by appending the type to the end of the number, e.g., 13U32, 2U8.
Oh, you just appending is like, okay. Okay, let's run it. Also Unicode character F32 by default, F64. I actually like it. Actually in C++ it's also by default F64, so but it's good. This is good. I think in many non C++ languages by default it's float, 32-bit float, F32. U8 12 by default is I32. Okay. And what is this? What is this? T. T.0, T.1. So indexing you can do indexing by dot. Okay, that's cool. Can I do just like this? Would it work? Integer bool doesn't implement format display. But what is this? Okay. Next.
Rust requires explicitness when it comes to numeric types. One cannot use a U8 for U32 casually without error. Luckily, Rust makes numeric type conversions very easy with the as keyword.
As keyword. As U32B. So A U8, B U32, A as plus 10. But this one did work. So literals, it's inferring the from literals B U52. So let's do as U8. So also works. 251. Familiarity will overflow. Which would overflow? Alright. So it's capturing overflow. I guess C++ will be able to capture overflow as well. What if I make it moot? And b plus equal 1 println b. Attempt to still detecting overflow. B equals 0. Maybe it's over. Oh my god. This is gonna be such a pain. It's a runtime error. I made it a runtime error. Right? Did it build it? Compiling prem run, finishing running. It's a runtime error. It's crashed. This is crashed.
Constants allow us to specify a common value that's used throughout our code many times efficiently. Instead of copying values like variables where they are used, constants directly replace the text identifier where they are used with their value at compile time. Unlike variables, constant must always have explicit types. Constant names are always in screaming snake case.
What is the difference between const and let? What the difference? Can I make the const const my crazy const equals 10? So do I need to specify the type? My crazy const will provide type. I need to specify the type. Dead con. My crazy const.
My crazy const.
Okay, it is compiling. What I was going to do, I forgot what I was going to do. Shadowing. Can I do shadowing now? F println my crazy const. Redefined. Okay, so I guess it's better to oh, and there are this screaming snake case. Oh my god. Okay, let's go.
An array is a fixed-length collection of data elements, all of the same type. The data type for an array is t, n, where t is the element's type, and n is the fixed length known at compile time. Individual elements can be retrieved with the x operator, where x is a usize index, starting at 0 of the element you want. Collections with a dynamic length, often called dynamic or variable arrays, are introduced in a later chapter about vectors.
So, do I need to put 3 here? Why I need to put 3 here? It's like there is a 3 elements here. Why I need to put 3 here? What if I put 2 elements here? It would yell at me. But it, you know. Can I emit it? One, two, three. Nums 1, 2. What is this? Can I remove it? With default parameters. Yes. and what it was. Colon question mark. I do not know why it's colon question mark.
A function has 0 or more parameters. In this example, the add function takes 2 arguments of type i32 signed integer of 32-bit length. If you just want to return an expression, you can drop the return keyword and the semicolon at the end, as we did in the subtract function. Function names are always in snake case. Hint, if you define a function, the data it accepts are called parameters. If you call that function and pass data to it, then it's called arguments.
If you call that add subtract. Can I omit? Can I omit this thing? No, I cannot. Oh my god. So why, if you just want to return the expression, you can drop the return keyword. Oh, so without semicolon it's a return. If x greater than 2, then else x minus y. Unnecessary parentheses around if condition. Okay. I do not know why we need that one. This is unnecessary too, by the way. And it's not happy. It's wants curly here. Rust. If this is unnecessary, this is unnecessary too. Where is the consistency? Oh, now it's not compiling. Oh yeah, because it wants these things. Man, I need the max. I cannot use this. Okay, what's going on? Unclose delimiter. Oh. Okay. Multiple return.
Multiple return values. Functions can return multiple values by returning a tuple of values. Tuple elements can be referenced by their index number. Rust supports various kinds of destructuring that we will see in many forms, allowing us to extract subpieces of data structures in ergonomic ways. Be on the lookout.
Okay. Ergonomic way. Swap. Oh yeah, so you can do this thing. Can you do const? Provide the type. Why for const you have to provide type, and for let you do not need to provide a type? Call in constants are limited to constant function, tuple struct and tuple variants. Oh my god, this is garbage language.
If no return type is specified for a function, it returns an empty tuple, also known as a unit. An empty tuple is represented by. Using is uncommon, but will come up often enough that it's good to know what's happening.
Returning nothing. Oh, so this is analog of void. Okay. This function will return if nothing is specified to return. Make nothing a b. It does print this stuff. What if I type 42, 52, whatever? Expected this found integer. Okay. Oh, my leg fell asleep. Chapter 1 conclusion.
Chapter 1 conclusion. Nice job so far. The basics of Rust aren't so bad, right? We're getting a peek into how the Rust compiler
It is
thinks.
bad. It
As a
is
system
bad.
programming language, it cares a lot about the size of values in memory, whether things can be modified or not, and making sure your math is what you want it to be. Next up, we'll be looking at some old friends, if tests and for loops. More resources. Chapter 2, Basic Control Flow. In this chapter, let's talk about basic control flow methods in Rust. If you are familiar with C-based languages, you'll feel right at home and maybe enjoy a surprise or two. If/else. Code branching in Rust is not surprising. Conditions don't have parentheses. Did we ever really need them? Our logic now looks nice and clean.
This is so proudly stated, but why we have curly here? Like why you put curlies here in this case, huh? Stupid.
Need an infinite loop. Rust makes it easy.
Why you have infinite loop? What's wrong with for colon or while true? Why you need infinite loop? What the point? Stupid. And you've got like a mutable fee. This it's like exam. What? How about for? I don't know. It's like this example is so bad also. Like I don't know, like for let x, I don't know, range 0 to 42. Something like this, I guess. Oh. While, oh, they don't need parentheses neither. Oh my god. How about for loop? Oh yeah, okay. So it's ranged base. Okay, so this is the ranges. Okay, for loop.
Rust for loop is a powerful upgrade.
Fine.
It iterates over values from any expression that evaluates into an iterator. What's an iterator? An iterator is an object that you can ask the question, what's the next item you have, until there are no more items. We'll explore this more in a future chapter. In the meantime, just know Rust makes it easy to create iterators that generate a sequence of integer numbers. The dot operator creates an iterator that generates numbers from a start number up to but not including an end number. The dot equals operator creates an iterator that generates numbers from a start number up to and including an end number.
Okay, I don't know. I'm not. It's syntaxes. It's fine. It's fine. Okay, let's see. 1, 2, 3, 4, 5, 4. Yeah, and 5 included. Makes sense. No parentheses. Whatever. Proudly. No parentheses.
Miss your switch statement. Rust has an incredibly useful keyword for matching all possible conditions of value and executing a code path if the match is true. Let's see how this works for numbers. We will have more to say in future chapters on pattern matching more complex data. I promise you it will be worth the wait. Match is exhaustive, so all cases must be handled. Matching combined with destructuring is by far one of the most common patterns you will see in all of Rust.
Destructuring. 1, 2. Why there is a pipe here? What's wrong with switch? Like why switch? Whatever. You don't want parentheses. It's fine. No parentheses, right? Case. Like what the difference? Like why did you want to have match here? X42. Found 42 number between 100 and oh, what is this? Found 1 or 2. Oh, it's a range. Number 3, 9 inclusively. We can bind the match number to a variable. Matched num found 42 between, so like if I put like a +1 here. Okay, so oh, and this is the binding, right? Match num. This is the default match. Not all cases are handled. Must exist default. Must exist. True. True. False. I guess it will yell, right? It should yell. I do not still not grasp the logic behind all the madness, but I think it did yell. Okay. And it would not yell if I delete this thing. Yeah. Loop can break or return a value. Huh? Why? Only loop? While x not equal 13. You cannot break with value in the while loop. Can only break with value inside loop. Or what? or breakable block. Use break on this zone without value inside the while loop break. Okay, I guess that makes sense because while can yeah, true. Anyways, I guess that makes sense. But why we need loop at first place?
If, match, functions, and scope blocks all have a unique way of returning values in Rust. If the last statement in an if, match, function, or scope block is an expression without a, Rust will return it as a value from the block. This is a great way to create concise logic that returns a value that can be put into a new variable. Notice that it also allows an if statement to operate like a concise ternary expression.
Yeah, this is good feature. Match. Yeah, that makes sense, I guess. Let's come look. Results without polluting function. Yeah, in C++ probably. Yeah, I would do this thing. Yeah. Guess it's okay. Yeah.
Hopefully I've shown a glimpse of Rust's power, even in the most basic language features. We'll be talking about for and match even more in depth as we gain more knowledge that can utilize their capabilities. Next time, we'll get into Rust's foundational data structures. Chapter 3, Basic Data Structure Types. It's time we explore beyond basic types. In this chapter, we will look at the most primitive data structures in Rust, paying close attention to their representations in memory. I think you will enjoy how little Rust hides from you how things work.
Structures. The struct is collection of field. Okay.
A struct is a collection of fields. A field is simply a data value associated with a data structure. Its value can be of a primitive type or a data structure. Its definition is like a blueprint for a compiler on how to lay out the fields in memory nearby each other.
So names are camel case. Okay. String is a struct. Animal type, name. Okay, that's fine.
Unlike functions, methods are functions associated with a specific data type. Static methods that belong to a type itself are called using the operator. Instance methods that belong to an instance of a type are called using the dot operator. We will talk more on making your own methods in future chapters.
Let's learn from I don't know, like in C++, I guess it would be like this. I don't know. Hello world is 12 character long.
Rust programs have 3 memory regions where data is stored. Data memory for data that is fixed in size and static, i.e., always available through life of program. Consider the text in your program, e.g., hello world, this text bytes are only ever read from one place and therefore can be stored in this region. Compilers make lots of optimizations with this kind of data, and they are generally considered very fast to use since locations are known and fixed. Stack memory for data that is declared as variables within a function. The location of this memory never changes for the duration of a function call. Because of this, compilers can optimize code so stack data is very fast to access. Heap memory for data that is created while the application is running. Data in this region may be added, moved, removed, resized, etc. Because of its dynamic nature, it's generally considered slower to use, but it allows for much more creative usages of memory. When data is added to this region, we call it an allocation. When data is removed from this section, we call it a deallocation. Creating data in memory. When we instantiate a struct in our code, our program creates the associated field data side by side in memory. we instantiate by specifying all field values within. Struct name. Struct fields are accessed using a dot operator. Dot memory details of our example. The text inside the quotes is read-only data, e.g. Ferris, therefore it is placed in the data memory region. The function call string : from creates a struct string that is placed side by side with the fields of C creature in the stack. A string represents text that can be changed and does this by creating memory on the heap, the text where it can be modified, storing a reference to that memory location on the heap, and storing it in string struct. More on this in future lessons. Finally, our two friends Ferris and Sarah have data structures that will always have fixed locations in our program, so they are placed on the stack.
So this is the struct. Sarah. Octopus Sarah. I wonder why it's not equal sign. Like this. Anyways. Okay. Struct location. Okay, I don't think I'm mad at this. Use like a tuple. I think it's fine. Marker. Struct do not have any fields at all, as mentioned.
As mentioned in Chapter 1, a unit is another word for an empty tuple. This is why this kind of struct is called unit-like. This type of struct is rarely used.
Rarely used? Species. This line prevents compiler.
Enumerations allow you to create a new type that can have a value of several tagged elements using the enum keyword. Match helps ensure exhaustive handling of all possible enum values, making it a powerful tool in ensuring quality code.
Yeah, it's forcing the capitalization. Okay, so this creates the sea creature. Very species: crab, octopus, fish, clam. This is a crab. Name, Ferris name.
Enum elements can also have one or more data types, allowing them to behave like union from C. When an enum is pattern matched using match, you can bind a variable name to each data value. Memory details of enum. An enum data value will have a memory size equal to its largest element. This allows for all potential values to fit in the same space of memory. In addition to element data types, if any, each element also has a numeric value that represents which tag it is. Other details. Rust enum is something also known as a tagged union. The combining of types to make a new type is what people mean when they say Rust has algebraic types.
Combining of types to make a new type is something else known as tagged union. Tagged union. enum. Species, person, size, weapon. Oh, what? Claw, poison, poison type. What the heck? What the heck is this? None. What? Sea creature species crab. String from arm, weapon. Weapon, claw, 2 size small, size. So this is the type. So you can put any type inside the enum. So enum essentially it's a union. Oh, okay. Oh, I see why it's called tagged union. So it's analog of variant, I guess. So enum. Sea creature. Match species. Crab match weapon. Num close size. Where did it get assigned? Ah, okay, so it's get assigned. So this is sort of variables. So size description. So if I would ignore the size description, right? So like match size. So let's remove this thing. Okay, so some intelligent prefix it with underscore. Okay, so I just put the underscore here and it would not complain. Okay, or I can do underscore size if I don't care about it. Okay. Type to make new type is what people's messages ask. Algebraic types. Type to make new types. I don't know. What does it mean? You stacking types together? Yeah, like what is the big deal with it?
How exciting. We now have the most basic tools for representing the form of our ideas in code. Hopefully now we can see a glimmer of how Rust's fundamental operations work in harmony and conciseness with its types. Next up, we will talk about a concept that gives our data types even more flexibility of representation: generics.
Okay.
Chapter 4: Generic types. Generic types are incredibly important in Rust. They are used in the representation of nullable values, i.e., variables which might not have a value yet, error handling, collections, and more. In this section, we will be learning about the foundational generic types you will likely be using all the time. What are generic types? Generic types allow us to partially define a struct or enum, enabling a compiler to create a fully defined version at compile time based off our code usage. Rust generally can infer the final type by looking at our instantiation, but if it needs help, you can always be explicit using the T operator, also known by the name Turbofish. He's a good friend of mine.
Turbo fish. I guess it looks like a fish. This is the fins, and this is the turbo fish. Partially defined struct type. Okay. Bug of holding. Turbo fish. Why this? Anyways. Float bug, bug of holding. Rust can infer type for generics too. That's good, that's better to do it. Never put a bug of holding in a bug of holding in real life. Why? Why never do this thing? Why I cannot do this thing? That's fine. Never put a bug. No, that's fine. Don't tell me never. Okay.
Representing nothing. In other languages, the keyword null is used to represent an absence of a value. It creates difficulty in programming languages because it creates the possibility that our program might fail when interacting with a variable / field. Rust does not have null, but it is not ignorant of the importance of representing nothing. Consider a naive representation using a tool we already know. This pattern of providing a non-alternative representation for one or many alternate values is so common in Rust because of its lack of a null value. Generic types help solve this challenge.
None represent the absence of the item of an item. Bug of holding item. Oh yeah, this is a new. Non-alternative representation for me. Like you can call it null, I don't know, like, or null with n capital. It's like what's wrong with null? So let's eliminate null and rename it to none. It's the same thing, just call it null.
Rust has a built-in generic enum called option that allows us to represent nullable values without using null. This enum is so common. Instances of the enum can be created anywhere with the enum variant sum and none.
Yeah, you need null. Just don't remove null and put none for instead of it. Like if you don't like null, go all the way through, or just be honest and keep null. Bug of holding item option. Oh, it's called option. It's not even called optional. It's fine. You can call it option. Bug holding nothing. We have specified the type because otherwise Rust would not know what type of bug it is. Is none. Okay, so what? Where did it get this function? Sum 42. Sum 42. What is sum? I guess it's constructor for option. Why not to do, I don't know, sum is a function, I guess. Why it's highlighted like this? Is it like a keyword? Is sum. What is in C++? Has value, I think, right? Something in the bug, nothing in the bug. Let's deconstruct option elegance. Ensure we handle of all cases. Dot item. Match dot I sum none. Sum v. Huh. I wonder how this is working. That's. Is it like a special case in the compiler, or like it's a library one? It's like a. It's dark, so I think it's a. I don't know. There is no includes, so it might be language construct. That means option is also kind of, or like it's tightly integrated with the compiler. Who knows? Found 42 in the bug. There is nothing in the bug. There is something in the bug. Oh yeah. Oh my god. I don't know. The language is so inconsistent. Why they decided to allow shadowing? Okay, let's go to next chapter.
Result. Rust has a built-in generic enum called result that allows us to return a value that has the possibility of failing. It is the idiomatic way in which the language does error handling. Enum result T E. Okay T. Error E. Note that our generics type has multiple parameterized types separated by a comma. This enum is so common. Instances of the enum can be created anywhere with the enum variants OK and error.
Okay. Okay error. Okay error. So this one creates result. Result. Do something that may fall. Result. Match result. Okay error. That's fine. Error, this is not the right number. Of course it's 42. 42. Font 13. Okay. Main has the capability of returning a result. Main return no value but could return an error. HDF profile. Device debugging for running. Error, something went wrong in main. I do not know who is printing it. Notice we use unit value inside the result. Okay, to prevent everything is fine. Unit value. Notice we use a unit value. Okay. So yeah, I noticed it. Graceful error handling.
Result is so common that Rust has a powerful operator. For working with them, these two statements are equivalent.
Do something may fall, much something that may fall, something that may fall. Oh, it's fall through. I do not know why we need this thing. Let's look at an example. V. Oh, there is a, oh, I see. There is a return here. Okay. So it's a fall through. I see.
Working with option/result can be tedious when you are just trying to write some quick code. Both option and result have a function called unwrap that can be useful for getting a value in a quick and dirty manner. Unwrap will get the value inside option/result. If the enum is of type none/error, panic. These two pieces of code are equivalent.
Panic. Dot unwrap. Dot unwrap. I know. I mean, here like a fall through, I think it's fine. Especially if you know error is a string. So that's how ugly. The language is so ugly. Unwrap. So what panic would do? Oh yeah, it's crashed. Okay. And there is a backtrace. I mean, crash is the best option because you can get the backtrace and find out why it's
Vectors.
crashed. If
Some
you
of the more
doubt
useful
crash.
generic types are collection types. A vector is a variably sized list of items represented by the struct vec. The macro vec lets us easily create a vector rather than manually constructing one. Vec has the method iter, which creates an iterator from a vector, allowing us to easily put a vector into a for loop. Memory details. Vec is a struct, but internally it contains a reference to a fixed list of its items on the heap. A vector starts with a default capacity. When more items are added than it has capacity for, it reallocates its data on the heap to have a new fixed list with large capacity.
Okay. So it has a static function called new turbofish. I mean, yeah, this is turbofish. So it's mutable, push, push, push. So they mentioned there is exclamation mark, push, push, push. So vec exclamation mark, and there is a two elements, string vec iter float vec string vec. Interestingly, it did not complain here. Those values were not used, I guess. Such a strange language. In why you need to provide iter? It's like, why you need to put dot iter? Can you do it like this? Oh, why it's needed dot iter? Why they put dot iter? I removed it and it worked.
In one chapter, we've learned how much power generic types give us. Don't worry if you don't know fully how to use everything. Right now, it's just good to be aware of the major ideas you will see again and again in code. Our functions are getting quite lengthy. In our next chapter, we will spend talk about an important concept in Rust, data ownership. Chapter 5, Ownership and Borrowing Data. Rust has a unique paradigm for managing memory compared to other programming languages. We're going to look at the behaviors and validations of the compiler one by one, so it's not overwhelming. It's important to remember that ultimately the rules we show don't exist to make your life hard, but to help you make your code less error-prone.
Famous 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 words. Look, sometimes when my son was little, I was saying, we were arguing, and I was saying, it's like, I want you for your benefits. And then the arguments were getting heated. He does not understand like why I want to do him what I want him to do. And then later on, I reflecting on all this stuff and thinking, it's like, maybe it doesn't matter too much. Obviously I want the best for him, but like maybe it's okay for him just to sometimes learn and fail and understand by himself. Anyways,
Ownership. Instantiating a type and binding it to a variable name creates a memory resource that the Rust compiler will validate through its whole lifetime. The bound variable is called the resource's owner.
okay, who is the owner? Who is the owner? Yeah. Okay, who is the owner? Scope-based resource management.
Scope-based resource management. Rust uses the end of scope as the place to deconstruct and deallocate a resource. The term for this deconstruction and deallocation is called a drop. Memory detail. Rust does not have garbage collection. This is also called resource acquisition, is initialization RAI in C++.
Yeah, this is drop is hierarchical.
Dropping is hierarchical. When a struct is dropped, the struct itself is dropped first, then its children are dropped individually, and so on. Memory details.
Yeah, that's
by automatically freeing memory, Rust helps ensure that there are fewer memory leaks. Memory resources can only be dropped once. Moving ownership. When an owner is passed as an argument to a function, ownership is moved to the function parameter. After a move, the variable in the original function can no longer be used. Memory details. During a move, the stack memory of the owner's value is copied to the function calls parameter stack memory.
Who is moved to do something? Dropped here. Who can no longer be used? What? 42. What? Second. This would not compile? What the heck? This thing ate it foo. What the freak? Look, everything on stack. Why are you doing this thing? You just can make the copy. It's like a I-32. Just make the copy. So stupid. Yeah, let's what is it? Println. Dot x. not a function. What it was? Oh, println exclamation mark. Oh, println. Foo dot x. Yeah.
Borrowing ownership with references. References allow us borrow access to a resource with the in operator. References are also dropped like other resources.
F is drops here, foo is dropped here. Test foo z zx. So we have a function. It probably would complain. Oh yeah, it should. Expected one of it's inverted this way, right? Profile. What is the warning? Oh, warning, but it's run. Okay, so test f expected foo found reference to foo. Cannot move out of foo because it's borrowed. Okay. Ownership with references. Something foo.
Borrowing mutual ownership with references. We can also borrow mutual access to a resource with the and mud operator. A resource owner cannot be moved or modified while mutually borrowed. Memory detail. Rust prevents having two ways to mutate an own value because it introduces the possibility of a data race.
Do something. The land dropped here. Mutably f at x 13. So it's would print 13, right? And then do something else. It will print 7 or 13.7 failure. Do something. Foo would fail because foo cannot be moved while mutably borrowed. So would fail because foo is not modifiable while mutably borrowed. Foo x equals 12. F is dropped here because it is no longer used after. So, like this would fail, right? But if I comment this thing out, it would work. Oh, it's still failing. Oh, I see. It is failing for different reason because it's never been used. But if I put like a fx equals 1 here, ah my god, semicolon, it would work. So strict, very strict dereferencing.
Dereferencing. Using and references, you can set the owner's value using the operator. You can also get a copy of an own value using the operator. If the value can be copied, we will discuss copyable types in later chapters.
Okay. So you can get the copy. You can get the copy, set the reference owner's value. You can. So bar is going to be copy. Okay.
Passing around borrowed data. Rust rules for references might best be summarized by: Rust only allows there to be one mutable reference or multiple non-mutable references, but not both. A reference must never live longer than its owner. This doesn't tend to be a problem when passing around references to functions. Memory details. The first rule of references prevents data races. What's a data race? A data race, when reading from data, has the possibility of being out of sync due to the existence of a writer to the data at the same time. This happens often in multi-threaded programming. The second rule of references prevents the misuse of references that refer to non-existent data called dangling pointers in C.
Okay, so what is this thing? With foo. It's captured by reference. Oh, okay. So you can modify. So this thing will borrow f, and then mutable references are dropped here. Okay. But you have to explicitly. How print is working? Yeah. Println. How println is working? Be used in pieces of references. Do something. Foo. Return. Y dropped here, foo is dropped here. X is dropped here, allow us to create non-mutable reference. Explicit lifetime.
Even though Rust doesn't always show it in code, the compiler understands the lifetime of every variable and will attempt to validate that a reference never exists longer than its owner. Functions can be explicit by parameterizing the function signature with symbols that help identify which parameters and return values share the same lifetime. Lifetime specifiers always start with e.g. ABC.
ABC. This parameter foo and return value share the same lifetime. Do something A. What? Start the lifetime specifier. X is dropped here, allowing us to create non-mutable reference. Do something. Explicit by parameterize the function signature with symbols that help identify which parameters and return values share the same lifetime. Why? I know. I think explicit lifetime. We don't need explicit lifetime. Multiple lifetimes.
Multiple lifetimes. Lifetime specifiers allow us to be explicit with certain scenarios. The compiler cannot resolve itself by distinguishing all of a function signature component's lifetimes.
B lifetime. Static lifetimes.
Stat lifetimes. A static variable is a memory resource created at compile time that exists through a program start to finish. They must have their types explicitly specified. A static lifetime is a memory resource that lasts indefinitely to the end of program. Note that by this definition, some static lifetime resources can be created at runtime. Resources with static lifetimes have a special lifetime specifier static. Static resources will never drop. If static lifetime resources contain references, they must all be static. Anything less would not live long enough. Memory detail. Modifying static variables is inherently dangerous because they are globally accessible to be read from by anyone, introducing the possibility of a data race. We'll talk about the challenges of global data later. Rust allows the use of unsafe locks to perform some operations that the compiler cannot make memory guarantees about. The R symbol 338, symbol 349, symbol 31F, symbol 348, symbol 354, macron, symbol 35B, symbol 33, symbol 307, symbol 35CU, symbol 336, symbol 353, symbol 356, symbol 34B, symbol 305, letter 1E61, symbol 334, symbol 349, symbol 347, tilde, symbol 309, grav T, symbol 335, symbol 33B.
There is
symbol
another thing is
symbol
called
354,
static.
symbol 31F, symbol 349, acute, symbol 346, letter 1A1, symbol 337, voiceless, symbol 31F, symbol 333, symbol 313, symbol 35D, N, symbol 336, symbol 328, symbol 33C, symbol 339, symbol 332, symbol 35B, O umlaut, symbol 335, symbol 31D, symbol 349, symbol 316, symbol 30F, symbol 33E, symbol 314M, symbol 336, symbol 321, symbol
Why
320,
did you
symbol 33A, symbol
break my
320,
text to
symbol
speech?
310, symbol 35C, I circumflex, symbol 337.
Rastonomicon. Secret static swordfish. Static variable can also be scoped to be a function. String literals have a static lifetime. String literal have a static lifetime. Static let message. Static string. What is? Oh, this is the lifetime. Static lifetime. String hello world. Have a static lifetime. Reference F64. This string literal because it's also static. I did not. Oh, I did. It's generate a warning. Message hello world. Message P. Message P. Message string. Secret. Type str. What is type str? Lifetime and data types.
Lifetimes and data types. Similarly to functions, data types can be parameterized with lifetime specifiers of its members. Rust validates that the containing data structure of the references never lasts longer than the owners its references point to. We can't have structs running around with references pointing to nothingness.
Have struct running around with reference point to nothingness.
Phew, congrats for making it through. I know it's a lot to take in, but you are well underway to becoming a Rustation. Hopefully, it's clear how Rust is a language aimed to solve many of these common challenges in system programming. Unintentional modification of resources. Forgetting to deconstruct resources. Resources accidentally being deconstructed twice. Using resources after they have been deconstructed. Data erased caused by writing to resources while others are reading from resources. Seeing clearly areas of the code where the compiler can't make guarantees. In the next chapter, we'll apply some of this knowledge as we look at how Rust handles text.
Text. How many chapters here? 9 chapters. So we are more than halfway through.
Chapter 6 Text. Now that we understand a bit how Rust thinks of memory, we are prepared to talk about text in more detail. Rust cares a great deal about international text and byte level concerns you might not be familiar with from other languages. That said, Rust has many great tools for managing those concerns.
Okay, string literals. String literals are always Unicode. String literals type are static str, means that a reference to places there, and slug mute me, this compiler will not allow modification. Statics means the string that is available there. This is a pointer to sequence byte that's always valid UTF-8. Memory detail. The Rust compiler will likely put your string.
The Rust compiler will likely put your string in the data segment of your program memory.
Okay. So at least it's UTF-8. Always Unicode. Yeah, I'm curious what it will print. 7. 1, 2, 3, 4. It's 4. You're lying to me. 3. Print. Yeah. It's UTF-8.
What is UTF-8? As more languages were used on computers, the world needed to represent more text characters than ASCII allowed 1 byte, only allowed 256 characters. UTF-8 was introduced with a variable byte length of 1-4 bytes, greatly increasing the range of possible characters. An advantage of variable-sized characters is text did not have unnecessary bytes for very common ASCII, only requiring 1 byte still in UTF-8. A downside of variable-sized characters is that character lookup can no longer be done quickly one constant time with a simple indexing e.g. my test 3 to get the 4th character. It's possible that the preceding characters could have variable widths, altering where the 4th character actually begins in the sequence of bytes. Instead, we must iterate through a UTF 8-byte sequence to understand where the Unicode characters actually begin in linear time. Ferris, I'm mostly just happy to have UTF 8 for representing emojis of my underwater friends. Trap galactips fish dolphin whale.
Escape characters. New line, carriage tab, backslash, null, single quote. Oh, it's not full list. Okay. Yeah. Do we need this? Can we do it like this? Yeah, I don't know why they put. Ah, okay. You can do multi-line things. That's nice. Row string. Oh, you can have row strings. R sharp. That's also nice. And you end with sharp. What if I assume you can do it like no? Huh. Ending with it's let's say this might otherwise confuse normal string literal like double quotes and backslashes. But if I put like a colon sharp here, it will break. How I can do colon sharp? They did not say. Include string to include text from local files in your program. Ah, that's nice thing. You can do hash include, right? um, just file name. Oh, and it will generate a string. So would we became star type? So it's, oh, maybe it's in compile time. It has to be valid UTF-8. So number of characters, start with, end with, for basic testing is empty. Find option unsize, that's the first position of some text. First word. What is this ampersand sign? A second word. So you can index it, right? But if you index it in between, what would happen? Let half crop. Yeah. Oh, it will fail. Oh. So it will fail real time. Oof. First word, second word. It will fail real time. Half crop. Oh. So I need to delete this stuff. Yeah. It's crashed. So it did print 7 and then crashed. Cool. Yeah, so it's print 7 and crashed and did not get to that place. Okay.
Chars. With so much difficulty in working with Unicode, Rust offers a way to retrieve a sequence of UTF-8 bytes as a vector of characters of type char. A char is always 4 bytes long, allowing for efficient lookup of individual characters.
Chars collect vect char. Chars should be 4. What is this? Chars 3. Oh, it says as in. Okay, so if I remove this thing, it will print the crab. Okay, I was like, what's going on here? Chars collect. I do not understand. I do not understand what is this.
String. A string is a struct that owns a sequence of UTF-8 bytes in heap memory. Because its memory is on the heap, it can be extended, modified, etc. in ways string literals cannot. Common methods. Push str to add more UTF-8 bytes to the end of a string. Replace to replace sequences of UTF-8 bytes with others. To lowercase slash to uppercase for k changes. Trim for trim space. When a string is dropped, its heap memory is also dropped. String has a plus operator that extends the string with a and str and returns itself, but it might not be as ergonomic as you hope for.
Hello world string pushter. Hello world, hello world, hello world plus. I know. Hello world.
Text's function parameters. String literals and strings are generally passed around as a string slice to functions. This offers a lot of flexibility for most scenarios where you don't actually have to pass ownership.
String literals and strings are generally passed around as string slice to function. This offers a lot of don't actually have pass ownership. Say it loud. Hello. Say it loud. Goodbye. Message to string to uppercase. To string to uppercase.
Concat and join are two simple but powerful ways for building strings.
So what did join provides okay. Format.
The format macro allows us to create a string by defining a parameterized string with placeholders for where and how values should be placed, e.g. Format uses the same parameterized strings of println. The capabilities of this function are too large of scope for Tour of Rust. Check out the documentation here.
To string.
Many types can be converted to a string using toString. The generic function parse can be used to convert strings or string literals into a typed value. This function returns a result because it could fail.
Result 4242 a string parse okay. Conclusion.
Now you know the basics of text. As you have seen, Unicode makes working with text a bit tricky, but the standard library has plenty of functionality to make it easy to manage. Up to now, we've mostly looked at Rust from the lens of procedural paradigm, i.e. just functions and data, but it's time we now talk about traits and the capabilities unlocked by Rust's object-oriented paradigm. Expressing ideas with functions is a proven way of representing behavior, and Data C has been doing it for decades. Historically, computer science has found other useful expressive aggregations and abstractions for data. You may be familiar with Object-Oriented Programming OOP as one such way. In this chapter, we'll explore the Rust programming language beyond functions. What is OOP? Object-Oriented Programming roughly refers to programming languages that have a number of iconic features. Encapsulation associating data and functions into the conceptual unit of a single type called an object. Abstraction hiding data and function members to obfuscate implementation details of an object. Polymorphism, the ability to interact with objects of different types through one interface. Inheritance, the ability to inherit data and behavior from other objects. Rust lacks inheritance of data and behavior in any meaningful way. Structs cannot inherit fields from a parent struct. Structs cannot inherit functions from a parent struct. That said, Rust implements many programming language features so that you might not mind this lacking.
How about interfaces? That's very interesting why they did not. Oh, there is interfaces.
Rust supports the concept of an object that is a struct associated with some functions, also known as methods. The first parameter of any method must be a reference to the instance associated with the method call, e.g. instance of obj.foo. Rust uses and self-immutable reference to the instance, and mut self-mutable reference to the instance. Methods are defined within an implementation block with keyword impl.
Ah. You could do it this way, right? Why you didn't do it this way? Rust? What the reason to add impl here? Huh. So stupid. Get sound. Creature, get sound. Bloop. Noise. I have a it's like missing lifetime specifier. I'm very confused. Somehow.
Abstraction with selective exposure. Rust can hide the inner workings of objects. By default, fields and methods are accessible only to the module they belong to. The pub keyword exposes struct fields and methods outside of the module.
Get sound, noise. That would work, right? Yeah. So I think it's between modules. Trait. Noisemaker. Noisemaker for C creature. Okay, so this is the sort of the way to have inheritance. So it's not, it's like a you're inheriting noisemaker for C creature. you're inheriting from traits, or trait is sort of interface.
Polymorphism with traits. Rust supports polymorphism with traits. Traits allow us to associate a set of methods with a struct type. We first define the signatures of methods of a trait within. When a struct implements a trait, it establishes a contract that allows us to indirectly interact with the struct through the trait type e.g. and in my trait without having to know the real type. A struct's implemented traits methods are defined within an implementation block.
Creature, make noise. Implement method on traits. For C creature, make noise. Make a lot of noises. Oh, that's interesting. So this is not implemented, but this is implemented and it's gonna work. So C creature, as soon as you implemented that method, but what if you have like multiple ones? Oh, let's test first this one. So that code, blah blah blah, right? And but what if I have unimplemented func? Do I need to implement all traits? All traits item implement missing unimplemented func. I guess no. Yeah, that makes sense. Traits can inherit methods from our traits. Oh, they they said, oh, you know, we don't have inheritance. We don't have inheritance, but we have traits which can be inherited. Noise maker trait. Yeah, here we go. This is the, and this one is implemented. Loud noise maker. Impl loud noise maker. Noise maker for. And okay, so if you comment this thing out, that would not work. Yeah. Okay. Blub blub blub. Dynamic and static dispatch.
Dynamic vs. static dispatch. Methods are executed in two ways. Static dispatch, when the instance type is known, we have direct knowledge of what function to call. Dynamic dispatch, when an instance type is not known, we must find out some way of calling the correct function. Trait types and in my trait give us the ability to work with instances of objects indirectly using dynamic dispatch. When dynamic dispatch is used, Rust will encourage you to put din before your trait type so people are aware. Memory details. Dynamic dispatch is slightly slower because of the pointer chasing to find the real function call.
C creature, noise maker. Static make noise. Dynamic make noise. C creature, noise maker. Noise maker. Yeah. So let's run it. That code. What is the that code name string? Println. Okay. So if I remove dynamic here, it's warning, but it did run, so it will warn, but
When we pass an instance of an object to a parameter of type, and in my trait, we pass what is called a trait object. A trait object is what allows us to indirectly call the correct methods of an instance. A trait object is a struct that holds the pointer of our instance with a list of function pointers to our instance of methods. Memory details. The list of functions is known in C++ as a vtable. Handling unsized data. Traits introduce an interesting challenge when we want to store them within another struct. Traits obfuscate the original struct, thus it also obfuscates the original size. Unsized values being stored in structs are handled in two ways in Rust. Generics using parameterized types effectively create struct/function known types and thus known sizes. Indirection putting instances on the heap gives us a level of indirection that allow us to not have to worry about the size of the actual type and just store a pointer to it. There are other ways as well.
generic functions.
Generic functions. Generics in Rust work hand in hand with traits. When we describe a parameterized type T, we can constrain what types can be used as an argument by listing what required traits the argument must implement. In this example, type T must implement trait foo. Fn my function t foo, t, where t colon foo. By using generics, we create static type functions at compile time that will have known types and sizes, allowing us to perform static dispatch and store as a size value.
Noise maker for C creature, so we implemented traits and generic make noise type T, where T is a noise maker. Rust have shorthand for expression generic constrained by trait. Foo impl foo. Okay. Impl noisemaker. You could like why not like this? Would it work? Wait, what? It did work. Why we need impl here? Is it just to give the hint to compiler to optimize? I do not understand. It's like it's a stupid. Why you did not call it pointer? Just to say, oh, you know, we don't have pointers, but we have boxes.
Chapter 7 Conclusion. We now have more language features at hand to represent our ideas clearly. Rust abstractions might be simple, but they are powerful enough to make working with code a joy. In this chapter, we caught a glimpse of smart pointers with Box. In the next chapter, we'll learn about how smart pointers can help us with other specialized memory situations. Resources. Chapter 8 Smart Pointers. In this chapter, we will demystify smart pointers. Let's explore into these data structures that let us interact with the lowest level of memory. Ferris says, don't feel overwhelmed by this chapter if you don't feel you can write your own low-level memory management code in one short read. This chapter is mostly to introduce you to some useful tools and give a glimpse at how they work. References revisited. A reference is fundamentally just a number that is the start position of some bytes in memory. Its only purpose is to represent the concept of where data of a specific type exists. What makes a reference different from just a number is that Rust will validate the lifetime of references doesn't last longer than what it refers to, otherwise we'd get an error when we used it. Raw pointers. References can be converted into a more primitive type called a raw pointer. Much like a number, it can be copied and moved around with little restriction. Rust makes no assurances of the validity of the memory location it points to. Two kinds of raw pointers exist. Const T, a raw pointer to data of type T that should never change. Mut T, a raw pointer to data of type T that can change. Raw pointers can be converted to and from numbers, for example, useis. Raw pointers can access data with unsafe code, more on this later. Memory details. A reference in Rust is very similar to a pointer in C in terms of usage, but with much more compiled time restrictions on how it can be stored and moved around to other functions. A raw pointer in Rust is similar to a pointer in C that it represents a number that can be copied or passed around, and even turned into numerical types where it can be modified as a number to do pointer math.
A as const I32 as usize. Data is here. A oh, okay. Pointer to const I32 64. Okay. So we get the pointer. Okay. Yeah, this is definitely more than 32. I have 32.
Dereferencing. The process of accessing / manipulating data that is being referred to by reference IE, and I32 is called dereferencing. References are used to access / manipulate data in two ways. Access to the referred data during assignment of variables. Access to fields or methods of the referred data. Rust has some powerful operators that allow us to do this.
The star operator is explicit way to dereference and reference. What the heck is this? What is this? 42. Ref A. They call it reference, but essentially it's a pointer. Yeah, I think arrow in C++ can be as well be applied to, like, oh, they said, oh, look at this, and but like C++ it happens for references, but you cannot, and you but you do not need to dereference references, get the reference automatically. um, but like explicit values you have to dereference in Rust. So essentially it's a pointers, but like in C++, I guess you can also convert not to have like arrow and have a pointer, but it's actually makes harder to implement smart pointers. Yeah, so like this is why you need arrow.
Smart pointers. In addition to the ability to create references to existing type data using the and operator, Rust gives us the ability to create reference-like structs called smart pointers. We can think of references at a high level as a type that gives us access to another type. Smart pointers are different in their behavior from normal references in that they operate based on internal logic that a programmer writes. You, the programmer, are the smart part. Typically, smart pointers implement deref mut, and drop traits to specify the logic of what should happen when the structure is dereferenced with and. Operators.
Okay. Smart unsafe code.
Smart unsafe code. Smart pointers tend to use unsafe code fairly often. As mentioned earlier, they are common tools for interacting with the lowest levels of memory in Rust. What is an unsafe code? Unsafe code behaves exactly like normal Rust, with the exception of a few abilities that the Rust compiler is unable to make guarantees about. A primary ability of unsafe code is dereferencing a raw pointer. That means taking a raw pointer to a position in memory and declaring a data structure exists here, and turning it into a representation of data you can use, i.e. const u8 into u8. Rust has no way to keep track of the meaning of every byte that gets written to memory. Because Rust can't make guarantees about what exists at an arbitrary number used as a raw pointer, it puts the dereference in an unsafe block. Smart pointers dereference raw pointers extensively, but they are well proven in what they do.
Pointers dereference raw pointer extensively, but they are in the way to do. Is a raw pointer getting the memory address of something as number is totally safe. Pointer as use size pointer A, that will remember location pointer A, pointer B, B, um, F32, I see. Okay. Familiar friend, Malok.
Familiar friends. Consider some smart pointers we've already seen like vect and string. Vect is a smart pointer that just owns some memory region of bytes. The Rust compiler has no idea what exists in these bytes. The smart pointer interprets what it means to grab items from the region of memory it manages, keeps track of where data structures within those bytes begin and end, and then finally dereferences a raw pointer into data structures into a nice clean ergonomic interface for us to use, e.g. my vect3. Similarly, string keeps track of a memory region of bytes and programmatically restricts content written to it to always be valid UTF-8 and helps dereference that memory region into a type and SDR. Both these data structures use unsafe dereferencing of raw pointers to do their job. Memory details. Rust has an equivalent of C's malloc, using alloc and layout for getting a hold of your own memory regions to manage.
Impl.py new layout from size align unwrap unsave allocate alloc and write secret recipe. Heap allocated memory.
Heap allocated memory. Box is a smart pointer that lets us move data from the stack to the heap. Dereferencing it lets us use the heap allocated data ergonomically, as if it were the original type.
Box new py heap py it. Ergonomically. Failable main revisited.
Failable main revisited. Rust code may have a plethora of representations of errors, but the standard library has a universal trait std:"error" for describing errors. Using a smart pointer box, we can use the type boxed in std:"error" as a common type for returning errors, because it allows us to propagate up an error on the heap and interact with it at a high level without having to know a specific type. Early in Tour of Rust, we learned that main can return an error. We can now return a type capable of describing almost any kind of error that might occur in our program, so long as the error's data structure implements Rust's common error trait. fn main result boxed in std:"error".
Okay. Air not fresh air. Not fresh air. Derive debug. He did not explain this stuff. Display for non. Yeah, so implementation display for non-fresh. Format. This py is not fresh. Formatter. Samaha. Byte. Box new, not fresh air. Referencing counting.
Referencing counting. RC is a smart pointer that moves data from the stack onto the heap. It allows us to clone other RC smart pointers that all have the ability to mutably borrow the data that was put on the heap. Only when the last smart pointer is dropped does the data on the heap become deallocated.
Reference counting. Some smart pointers are dropped now. The heap data py finally deallocated. Clone. Clone. Sharing access.
Sharing access. RefCell is a container data structure commonly held by smart pointers that takes in data and lets us borrow mutable and immutable references to what's inside. It prevents borrowing from being abused by enforcing Rust's memory safety rules at runtime when you ask to borrow the data within. Only one mutable reference or multiple immutable references, but not both. If you violate these rules, RefCell will panic.
There is a that takes in data and lets it borrow mutable and immutable reference. Prevents borrowing from being abused by enforcing Rust memory safety rules at runtime. You ask to borrow the data within safety rules at runtime. So we've got PyCell, RefCell new. RefCell validates memory safety at runtime. PyCell is not mute. Borrow mute. What? It. hit slices. What the heck? Now we can borrow immutable once our mutable references drop. Ref_pi. I'll borrow slices left. So we started with 8 slices. I think I've got desensitized by idiocracy of Rust.
Sharing across threads. Mutex is a container data structure commonly held by smart pointers that takes in data and lets us borrow mutable and immutable references to the data within. This prevents borrowing from being abused by having the operating system restrict only one CPU thread at a time to have access to the data, blocking other threads until that original thread is done with its lock borrow. Multithreading is beyond the scope of Tour of Rust, but Mutex is a fundamental part of orchestrating multiple CPU threads accessing the same data. There's a special smart pointer arc, which is identical to RC, except uses thread-safe incrementing of reference counts. It's often used to have many references to the same mutex. Combining smart pointers. Smart pointers might seem limited, but they can make some very powerful combinations. RC vec foo allow the cloning of multiple smart pointers that can borrow the same vector of immutable data structures on the heap. RC ref cell foo allow multiple smart pointers the ability to borrow immutably the same struct foo. Arc mutex foo allow multiple smart pointers the ability to lock temporary mutable/immutable borrows in a CPU thread exclusive manner. Memory detail. You'll notice a theme with many of these combinations: the use of an immutable data type possibly owned by multiple smart pointers to modify internal data. This is referred to as the interior mutability pattern in Rust. It is a pattern that lets us bend the rules of memory usage at runtime with the same level of safety as Rust's compile time checks. Smart pointers are the idioms of Rust programming and let us not have to recreate the very common patterns of memory usage. With them, you are ready to tackle the toughest of challenges. Now that we have the foundation of Rust, let's talk a bit about how we make larger projects. In Chapter 9, we break free of single-page lines of code. Chapter 9, Project Organization and Structure. So far, all of our code examples have been a single file. Let's discuss how our code can be better organized and shared by others. Modules. Every Rust program or library is a crate. Every crate is made of a hierarchy of modules. Every crate has a root module. A module can hold global variables, functions, structs, traits, or even other modules. In Rust, there's not a one-to-one mapping of files to the module tree hierarchy. We must build the module tree explicitly by hand in our code.
Like, why? Why not make the file module?
Writing a program. A program has a root module in a file called
main RC, and there is no way to call it differently. The library has a root module in the file called librc. It's like you're forcing file naming, but like I don't know where is the I don't have
referencing other
words
modules and crates.
to
Items and modules
be
can be
angry
referenced with their full module path
express my
std:/f64:constants:_pi. A simpler way is the use keyword. It allows us to specify particular items from modules we want to use throughout our code without a full path. For instance, use std:/f64:constants:_pi allows me to just use the identifier pi in my main function. std is the crate of the standard library of Rust, which is full of useful data structures and functions for interacting with your operating system. A searchable directory of crates created by the community can be found at When we think of code, we usually imagine a hierarchy of files organized in directories. Rust lets you create modules closely related to your file structure. There are two ways in Rust to declare a module. For example, a module foo can be represented as
Okay. Okay. Okay.
a submodule can be directly inlined within a module's code. One very common use for inline modules is creating unit tests. We create an inline module that only exists when Rust is used for testing.
I don't care too much about modules. Whatever. Yon Prelude. Chapter 9.
You now have a few tricks up your sleeve when it comes to creating Rust applications and libraries ready for the world. Don't
The
worry
end.
about remembering it all. As your library grows and is used by other people, you'll find what works best at each milestone. Resources. It's been a joy to have you on the Tour of Rust. Ferris and the Tour of Rust team sincerely hope you enjoy the journey ahead. If you have felt comfortable this far, we strongly recommend diving deeper with these resources.
I think I will start trying to write something in Rust. SDL Rust. SDL Rust. Okay, getting started. So project plus Rust Tetris. Getting started. So I think I need to create main.rs, right? Copy. How to compile. How to compile Rust code in Linux. World Rust programming language. So projects and project make dir hello world cd make Rust program basics Rust C main rc. Let's make file Rust Tetris main.rc. I think it should be lowercase. Rust C main.rc, right? So let me. Oh, it is lowercase. Okay. Compile. Stern create. Cannot find create. Okay. Create is the L2. How to install SDL to create in Linux. Rust SDL to create access. You must first install native SDL device and add the crate to your cargo toml file. Oh, cargo new. Oh, I see. So let's delete this thing first. And cargo new Rust Tetris. Create binary application Rust Tetris. Oh my god. Oh my god. Cargo toml and add dependencies. But I do not know what version it is. How to compile it? I thought I just oh my god, that's so it's created directory here, like can I move it up? It's like, let's move it up. So okay, let's delete this thing. Yeah, Rust makes me like, why you created source directory here? Okay, how to compile Rust code in Linux? It's nothing. It didn't say anything about cargo and stuff. Rust C. How Rust code in Linux? With cargo build, cargo build. So I just run cargo build. Source cargo build What are you doing? Package list rustmon available from Melpa. Install. Updating creates IO index. Are you out of your mind? Why it takes so long? Cargo build 99% of CPU. What are you doing? What the heck? And nothing, no printage. It's not printing anything. Updating creates IO index. So, how is your life? How is your new year? You having fun? I don't know what it's doing. It's not saying anything. Is it hanged? Is it... Oh. Oh no, it's still running. It's using only one CPU. System monitor. Yeah, it uses only one CPU. No movements here. 98%. How long to wait? There is nothing. It says updating creates IO index. That's it. Let's ask Gemini. How long to wait? If you see no progress over 10 minutes, it's likely stuck due to network timeout or corrupted local cache. Check the connections you are behind the restrict firewall, clear the cache. Why there is a no, like, why it's not showing me any updates? Is it downloading anything? It's hard to say because I'm streaming. It does not look like there is a download. There is some download rate, but it's less than megabit. I guess I'll kill it. Stop compilation. Cargo build. So let's run it from the Rust Tetris cargo build. Waiting for file lock on package cache blocking. Updating. Oh, okay. maybe my Emacs terminal was like freaking out because it's doing like ASCII sequences. What the name? And curses. So probably I'll build like a hello world, and then maybe I'll try to build test SDL, like boilerplate SDL code, and then end the stream. That's insane. I think with Rust C, I was able to write a source. If I do Rust C main, yeah. I don't know why I need car. Oh, because of HDL. Stupid. Like, what's wrong with just a make file build system? I mean, I would love I would love, but like this is like why it's doing all this stuff. It's like it's good to have a good build system, but like takes forever to build. Come on. I think this just then you haven't run it, so it need to update the package. Yeah, I hope it's like a first time, and hopefully next time it's going to be faster.
I think this is just when you haven't run it, so it needs to update the package index.
But still, like I guess it's doing Git one, right? No, it did not run Git. It's doing something else. It's cargo build. So it did not does not look like it spawned any processes. It's a root process. So it's doing some stuff internally. Anyways, we're halfway through 60%. I already built Hello World by using Rust C, but I want to integrate SDL2 and just want to make it work out of box, and probably like a proper way to do Rust, I guess. Is it with cargo? Yeah, it's like uses 100% of CPU. It's using CPUs, like why not to make it multi-threaded? It's oh yeah, it's I guess it's There is no disk activity, there is no network activity. It just using one CPU, it could do like 16 times faster. And what is the 50 half a million indices? What is it? It's like a packages, files. Come on, I want to go sleep. Just hello. I mean, hello world build like SDL2. Crazy, half a million of packages. SDL2. Like what is this running loop? What is this? Why there is a two dots here? Is it not like a full code? Right, because yeah, you will leave it most of the time. This will be main loop. Reading user input, writing game logic. Must have gotos. Alright. It looks like for event in event function forever. Match event. Quit. Key down. Escape. Break to running. Oh, so it's breaking into running. Oh, I see. So like if you have, oh, okay, so it's fine. So that's actually a good thing. So if you have nested loops, you can specify what nested loop you want to break in. Yeah. Yep, I've got it. I've got it. I've got the idea. Oh, we done. I think we done. So cargo toml. Where is the executable? Oh, libc cannot build because it requires Rust C1 or new, while the version 161. We stuck in a pickle. Okay, so how to solve this? It looks like it hit command with smash your progress specifically as a critical the system is currently running. Since Rust evolves quickly, many for how to fix Rust setup updates table. Oh my god. Okay, let's try cargo build. Okay, Rust Tetris. Where is it? Oh, it's in debug. Target, debug, Rust Tetris. Yeah. I want to do it separately because I want to run it in debugger. This is so Rust Tetris. So this is cargo build. Hopefully it would do thing. Yeah. So what the path is: target, debug, Rust Tetris. Yeah. So let's put the snippet code. Oh, so we can delete this thing. And hopefully we can go sleep. Where is the code? There is no button to copy. Okay. Is it like this fast? What? It's compiled really fast. Okay. Const width equals 10. Oh, I need to. Oh my god! And it has to all capitals. I32. 8. So const cell size I32. Let's do 40. So let's call it Tetris in Rust, and it's gonna be width times cell size, height times cell size. Let me do wrapping like this. And I think that's it. It's not happy. 2 previous errors. Oh my. Expected U32 as U32 as U32. Expected I32 found. Oh my god. That's fine. 3, 1, 2, 3, 4. Right? So maybe that's alright. Okay. Compiled. Oh, yeah, width height. Hey, I think we can make it a bit bigger. maybe 50. So height is 20. So let me do calculator. So we have 1080 divided by 20. So 50. 50 is good, I guess. Yeah, it's big and juicy. Okay, let's change the color and call it a day. So draw color RGB, let's do 30, 22, 25. Here we go. Okay, that's it. I'm done with this stream. Thank you for watching, and hopefully see you next time. Bye.